Our test review for test number 1 in Calc 3. First thing we want to do is just create a couple vectors. So we got 3 points. We want to find the vector between those 2 points, or so on. So let's say P and Q. So you have point P, we have point Q. We're finding vector PQ, point and our terminal point. So the way we always do it is to find vector PQ, or terminal minus the initial. Okay. So in this case, we're going to end up with -2, -2, 1. And then if we want to find vector PR, in this case now R is our terminal point, we would get 1, -7, 3. And finally, if we want to do QR as our vector, Q now being our initial point, R being our terminal point, again doing terminal minus initial, we would end up with 3, -5, 2. Product between vectors PQ and PR. So you should be able to do this. In this case, we're going to set up this determinant, in which case we go I, J, K for the first row. The second row would be vector PQ, which is -2, -2, 1. And the third row would be vector PR. Remember, this order is very important because the cross product is not commutative. The order does matter. So then when we do this, what do we say? We say, okay, we go with I, and here's our 2 by 2 matrix that we're going to work with. And we do the determinant of that 2 by 2 matrix. And so we would get -6 minus -7. So this minus this. Okay. Then the next thing we're going to do is do our J, but remember we have to switch the sign on that, so we'll put a minus here, and then we use these 2 values and do that 2 by 2 determinant. So this times this minus this times this. So in that case, we're going to get -6. That's my J. And finally, we're going to do the K, which would be these 2 right here, in which case we're going to get 14. By all that, you got your cross product to be 1. In which case we'd write I plus 7J plus 16K, or we can do the bracket notation. It really doesn't matter. Practice doing dot products and triple scalar products. Okay, so let's do dot product first. It's very simple. So if we do this dot product, PQ to look at PQ, which was -2, -2, 1, and we're going to dot that with PR, which was 1, -7, 3. All you do is you multiply consecutive that's a 1 there, that's a comma. So in this case, we're going to get -2 plus 14 product. Scalar product. Okay. So our triple scalar product here is when we combine the cross product and dot product. All right. And so if we're going to do that, what we can do is you say, all right, well, we already have the cross product between PQ and PR, and then we could dot that with QR. So since we already did this work, we could just now do a dot product and we're done. Or if you didn't have that work set up ahead of time, which might not happen, we can talk about doing this whole thing at once. And we do this whole thing at once by doing this determinant of a matrix where each row is one of those vectors. And so we could say, all right, well, here's 3, -5, 2. That's the QR. That's what we're going to dot with. And then the cross product will line up the same way the cross product would in row 2 and row 3. So -2, -2, 1, or 1, -7, 3. Basically, this first row is the IJK, but instead of writing IJK, you write one of the other vectors. Now, one thing we talked about is that the order in which you put these 3 vectors in, here, here, and here, does not necessarily matter if we're applying this triple scalar product to a volume, which it could be, right? One use for the triple scalar product is to find the volume of a parallelepiped. So it's this box where you have these three vectors, and then those three vectors essentially create this box. Let's see if I can do it pretty neatly. There you go. And you want to find the volume of that box. This is the way to do it. And if you're talking about the volume of a box, you know the answer is always going to be positive. One thing that can happen is when you juggle these rows of this determinant, your answer could change sign. You could have a negative or a positive answer. The absolute value will always be the same, but the sign might change. So if we're going to ignore the sign, then it doesn't matter what order we put these rows in which case you would probably want to put the vector that has the most zeros in this top row to make your computation easier. But if you didn't do that, it's not a big deal either. In this case, we don't have any zeros, so I just placed it in order of the way the triple scalar product was set. Here's my dot product. Here was my cross product. Okay. Either way, what you would do here is you would say, all right, well, we have the first one, 3, and we have this 2 by 2. Okay, then we have the next one, 5, and we have this 2 by 2. Then the next one, 2, and we have this 2 by 2, just like you would with the ij and k. Instead of writing ij and k, though, you would write 3, negative 5, 2 in those exact same spots. So what would we get? Well, we would get 3 is my I. That's going to multiply by this 2 by 2. It's going to turn into, what do we have again? That's going to be negative 6 minus negative 7. And then we're going to switch the sign on this middle one still. That's going to then be negative 5 as my j. And that's going to multiply by the other 2 by 2, which remember we already did was negative 6 minus 1. And then the final one is the 2. And the next 2 by 2, which again we've already done, was 14 minus negative 2. So in the end, when you do this all out, what happens is you get 3 minus 35 plus 32. Which ultimately gives you 0. Now, that's fine. In terms of the volume we're working with, what does that tell us? If we wanted to use the triple scalar product to calculate a volume, now that's not guaranteed you have to do it, but if that's what we wanted to use the triple scalar product for, that would tell me that all of these vectors, 1, 2, 3, these three vectors, are basically all lying in the same plane, so that there is no box, there is no volume. So this vector here isn't going to give me the height of the box. It's sitting in the same plane as these other two, and therefore I can't get a box, which can happen. That's possible. Okay. Think about what are some of the other uses of some of the things we just talked about. A dot product. You can use a dot product to help you find the angle between vectors. Cross product. What can you use that for? To find a vector that's orthogonal to both vectors in your cross product. So not only do you need to know how to calculate these things, but you need to know what they're used for. Angle between these vectors PQ and PR. So we're just going to keep using the same vectors, recycling them for each question. So remember we have this formula, cosine of theta equals V over magnitude of V, magnitude of W. That's for the two vectors V and W, and that will help me find the angle between vectors V and W. Okay, that's the angle in between those two vectors. So in this case, our vectors V and W are PQ and PR. So we just simply plug what we have in, already calculated. We already did the dot product, so we know the dot product is going to be 15. We have to calculate the magnitude of PQ and magnitude of PR. So magnitude of PQ, PR. Of 4 plus 4 plus 1, so you square each component, add them together, take the square root, and this one will be the square root of 1 plus 49. Again, because we're squaring each component of PR. And in this case, we're going to get, what, square root of 9, which is 3, and here we're going to square root of 59, which you can't really do much with. So this will be 3 times the square root of 59. Now, we want to figure out what the angle is. So now we got to get rid of the cosine. The way we do that is with an arc cosine. So we say theta equals the arc cosine of 15 over 3 square root of 59. And for all intents and purposes, that's the answer. That's the angle, okay? And that's perfectly fine to say the angle is arc cosine of 15 over 3 square root of 59. And we could simplify that, I guess. Cancel the 3 with the 15, write that as a 5. But nonetheless, that's our angle. Now, that doesn't give you a whole lot of information if you're really trying to figure out what angle are we talking about. I don't know that anyone can visualize the angle based off of that calculation there, but that is the exact value of the angle. If we plug it into our calculator, make sure your calculator is set to degrees, you would say that the angle is roughly 49.39 degrees. That's what happened when you would take the arc cosine of 5 over square root of 59. And that's probably going to be more beneficial. So about 50 degrees is about the angle. Now you got an idea of the relationship between angle for vectors PQ and PR. We were talking about the angle between planes instead of angle between vectors. Well, you would use the same formula. Think about it. When you look at a plane, you should be able to pick out the normal vector of a plane very easily. All right? It's the coefficient. And then once you have that, the idea is, all right, well, the angle between the normal vectors to the planes would be the same as the angle between the planes themselves. So we use the same formula just with using the normal vectors to the planes. Parametrization of the line through 1, 0, negative 3 and parallel to PQ. So remember, PQ is the vector negative 2, 2, 1. Okay? So the two things we need are the two things that are given. Sometimes it's that easy. Sometimes it's not. Sometimes we got to do a little bit more work. But in this case, if we use our formula, x equals x1 plus at, y equals y1 plus bt, z bt, where x, y, and x1, y1, z1 are the point, in that case we're there, and ABC is the vector parallel to the line, which we have there, we have everything we need. Sometimes you got to figure out how to find the vector parallel or how to find the point. In this case, everything they gave us is what we needed, so factorization would be 1 minus 2t, 0 plus 2t, negative 3 plus t. And vector parametrization if you wanted to as well. We could write it as a set of parametric equations, but we also know vector parametrization, in which case we could say it's this vector valued function where the components are 1 minus 2t, 2t, and negative 3 plus t. Of doing it just in a vector valued function as opposed to a parametric set of equations, either one's acceptable. At this point we know both, so you could use either. Equation of the plane through, I'm kind of missing that word, it should say point, so this point's on the plane, and perpendicular to this line. Looking at this line, you should be able to pick out the vector that's parallel to that line. And the vector parallel to that line right here would be the vector 4. How did I get that? The coefficients in front of t are my a, b, c, similar to what we just did in the last problem. Now, if that vector is parallel to this line, and this line is perpendicular to my plane, then this is perpendicular to my plane, or normal to my plane, if you want to say. So that is your normal vector. What do you need to write the equation of the plane? You need a normal vector, which we now have, and we need a point on the plane. So what are we going to use? We're going to use this formula, a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. In this case, a, b, c is my normal vector, and x1, y1, z1 is my point on my plane. So just fill in what we have, and we're done. So 3 times x minus 2 minus 1 times y minus 0 plus 4 times z minus 1 equals 0. There's your plane. That's your standard form. We can also write our general form by distributing all this out, collecting like terms, in which case we would get 3x minus y plus 4z. Then we'd have a minus 6, we'd have a 0, and we'd have a minus 4. Collect all those constants. we would end up with 3x minus y plus 4z, and then minus 10 equals 0. So there are two acceptable ways to write your answer here. This one and this one. I don't care which one you use. Doesn't matter to me. They're both acceptable, standard form and general form. You should be able to go either way with it. By some equations. So we look at the equation and know what we're looking at and give a couple of details of what it is. So in this first one, it's pretty easy. It's based off of really the last question. If you notice, it's the same form. This has this ax plus by plus cz plus d equals 0 form, which is a plane. Okay, this is a plane. And details, it's a plane with normal vector 3, 4, negative 5. Give too much more detail there. I guess I could find some points on the plane too by, plugging some values in and satisfying, whatever z would be to make this work. Not necessary. I think this is more than enough detail here of what you would need. It's a plane, and it's had a normal vector 3, 4, negative 5. That's the most you can get out of this without putting too much work into it, and that's all I really would be looking at. All right, now we look at this one. Well, this one's not a plane, right? So we have to figure out what this is. We got quadratic in all variables, so we're going to have to do a little completing the square to kind of see what this ends up being. But nonetheless, we're going to have to identify what it is.
Oh, here we go, one more. So we want to identify this equation. Largely, you should kind of be used to this by now. You should realize that this is most likely going to be some sort of sphere type equation. We got the three squares, x squared plus y squared plus z squared. They're all positive, but we just got to put it in the right form. So completing the square comes into play here. We put our x's together, x squared plus 9x. We put our y's together, y squared minus 2y, and then the z squared plus 10z. And we're going to dump this 19 to the other side. So now what we want to do is we want to take this 9 and divide it by 2 and add it in with the squares. So we get 9 halves squared. Take this negative 2 and add it in with the y's. So that's going to be negative 1 squared. And take this 10 and add it in with the z's. So that's going to be 5 squared. Now what we just did is we added 9 halves squared, negative 1 squared, and 5 squared. So we're going to add that to the other side. So we have this negative 19. We're going to add, what is this going to be, 81 over 4. We're going to add a 1, and then we're going to add a 25. So on this side, this is written as now a square, x plus 9 halves squared. This is written as a square, y minus 1 squared. This is written as a square, z plus 5 squared. This all adds up together to give me 109 over 4. And so we could say characterize the graph, identify the equation, whatever the instructions are. This is a sphere. So you should clearly see this as a sphere. It's a sphere with center at negative 9 halves, 1, negative 5, and with a radius of the square root of 109 over 4, or we could say the square root of 109 over 2. Okay, so that should be a pretty easy one if you can complete the square. Alright, so that's your review. Make sure in addition to that you also look at curvature and know how to calculate curvature, and also arc length. Those should be pretty simple questions, so I don't think there's a need for me to put that into the review itself. So look at your homework questions, look at the stuff we did in class. So now we're on to these vector value functions. So looking at this vector value function, r of t, it's a three-dimensional vector value function where we have the three components, e to the negative t, 1 over t, t over t squared plus 1. So the first is we want to find the domain. So if you think about the domain of each of these individual functions, so we have e to the negative t, so that function has a domain of all real numbers. 1 over t has a domain all x except, say, x equal to 0, or sorry, t, all t not equal to 0. And then t over t squared plus 1 has a domain to be all real numbers as well. And so the domain of the vector value function is the intersection of all these domains. So the domain of R of t is all t such that t does not equal 0. We could write that a bunch of different ways. I could use interval notation. I could use set builder notation, but nonetheless, that's the domain. All right, so then we want to find the limit as t goes to infinity for R of t. Well, we have to do the limit as t goes to infinity of each component function. So doing this, we look at each one. So e to the negative t is really the same thing as 1 over e to the t. And as t goes to infinity, this denominator is going to go to infinity, and 1 over something that goes to infinity goes to 0. Same deal with this one. We get 0. Now here, if we get the numerator is going to go to infinity, the denominator is going to go to infinity, and so one thing we can say is L'Hopital's rule, infinity over infinity. So we could apply L'Hopital's rule, take the limit as t goes to infinity. The derivative of the numerator is 1, derivative of the denominator is 2t. Now the denominator is going to go to infinity as the numerator stays constant, so we get 0. You could also just said, well, the degree here is 1, the degree here is 2. This is bigger, degree in the denominator is bigger. As you go to infinity, the answer is going to be 0. So anyway, the limit as t goes to infinity of R of t is the vector 0, 0, 0.
I want to find the derivative and integral for this vector value function. I'll do derivatives and integrals. Remember, we have to take the derivative of each component of this. It goes for integration. So if I'm going to find the derivative of R of t, take the derivative of e to the negative t. That's an easy one. Negative e to the negative t. Well, if you write e as t to the negative 1, it's just power rule, so negative 1 over t squared is what you end up with. And then finally, we have t over t squared plus 1. Well, that one's going to take a little bit more time, but still pretty easy. You're going to use quotient rule. So derivative of the numerator is 1 times the denominator is t squared plus 1. And that's your derivative. That's your tangent vector. Okay? We're going to have what? Well, this will be negative 2t squared, and we have 1t squared. So we'll have 1 minus t squared in the numerator, and t squared plus 1. You want to take the integral of each exponent to do the integral of the integral of t over but you end up with 1/2 the integral of du like 1 over t dt, du logarithm, so 1/2 log u, u the integral going to be? The integral is going to be this vector f plus c1 different c value. But if you can integrate and differentiate, this should be no big deal.
Okay, for this one, we want to look at this and say, well, what are we looking for? So, if a particle has an acceleration vector given to be negative 32k, and we have this initial condition of v of 0, ignore the fact that initial is spelled wrong. So we have this initial condition that the v of 0 equals 3i minus 2j plus k, and r of 0 equals 5j plus 2k. We need to find the velocity and the position vectors. So we know that the velocity is the first derivative of the position function, and acceleration is the second derivative of the position function, or we could say the derivative of the velocity. So what we're trying to do is go backwards. So if we're going backwards here, we're going to have to integrate the acceleration vector to get the velocity vector. So the integral of the acceleration vector is going to give us the velocity vector, and the velocity vector should end up being, well, there's no I, so they consider it as 0, so the integral of the I component would be just c1. There's no j component, so that's considered to be 0, so the integral of 0 is a constant, so that'll be c2. And then negative 32k is your k component, so the integral of that's negative 32 t plus a constant, so let's say c3. Now to improve that, we're going to use this, and the fact that the first component here is 3 when t equals 0. So if t equals 0, then c1 has to be equal to 3. Well, since there's no t's there, this is just saying c1 equals 3. Same thing for c2. c2 is equal to negative 2. Then the last one is a 1, and this whole thing has to be equal to that 1. And so that's giving us that negative 32t plus c3 has to equal 1. But remember, t equals 0. So if t equals 0, we end up with c3 equals 1. And so our velocity vector, v of t, can be better written as 3, 2, negative 32t plus 1. Alright, so then we want to find the position vector. Now the position vector is just going to be the integral of the velocity vector. And that's your original position vector. And so that's going to end up being integral of 3, which is 3t plus some constant, let's say c4. Then the integral of 2, which is 2t plus c5. And then the integral of negative 32t plus 1, which would be negative 32t squared over 2, which gives us negative, 16t squared plus t plus c6. And so now we use this information here. This is saying when t equals 0, the first component I is 0, because there's no I sitting there. The second component is 5, and the third component is 2. So first, when t equals 0, we know that 3t plus c4 has to equal 0. Well, remember, t equals 0, so then this is gone, so c4 is 0. When t equals 0, this 2t plus c5 has to equal 5. And so, remember, t equals 0, so that's gone, so c5 equals 5. Then the last one is here, and so when t equals 0, that has to equal 2. So by default, you see right away c6 equals 2. And so our position vector, based off of this condition given, is going to be 3t plus 0, so we can just say 3t. Then it's going to be 2t plus c5, which is 5, and then negative 16 t squared plus t plus c6, which is 2. And so the question said, what's the velocity vector based off of these conditions? What's the position vector based off of these conditions? Those are your answers. Okay, so here we have the final one, which is the big one, which is to decompose the acceleration vector into the tangential and normal components. So ultimately, we want to be able to write the acceleration vector a as a sub t, t plus a sub n, n. So we have to find all these components. First, we want to find the acceleration vector. So the acceleration vector is the second derivative. So we have r. We need to find r prime. So r prime is pretty easy to find. It's going to be 1. It's going to be t. And it's going to be 1/2 t squared. And we're just taking the derivative of r itself. So then we have r double prime, which is this acceleration vector that we're trying to decompose, but we have to find the acceleration vector first. And so that's going to be 0, 1, and t. At at 1, that's the t value we're working with, the acceleration is going to be 0, 1, 1. And so ultimately, when t equals 1, we want to decompose that particular vector. So in order to do that, we have these 4 components that we need to find, a sub t, t, a sub n, and n. And essentially the idea is we have this vector here, which is this a sub t, t vector. We have this other vector here, which is a sub n, n. They're orthogonal to one another always. And so what we did is the sum of those 2 vectors is this diagonal here, and that's the acceleration vector. So we were able to break the acceleration vector up into these 2 separate ones, one acting as describing the change in the speed, the other one telling us what the change in the direction is. All right, so first thing we want to do is find t. So t is r prime over magnitude of r prime. Now at a half, or sorry, I keep saying a half, at 1, okay, r prime is going to be 1, 1, a half. And the magnitude of that is going to be 1 plus 1 plus a fourth. So that's going to give us, what's that going to give us? That's going to give us 1, 1, a half. And this is going to be 2 plus a fourth. 2 plus a fourth is 8 fourths, 9 fourths. Square root of 9 fourths gives us, what, 3/2. So if I flip and multiply, this is going to give us 2/3, 2/3, and 1/3. And so that's going to be your unit tangent vector at 1. Okay. So the next thing we want to do is find a sub t. Well, that's a dot t. And so at 1, the acceleration vector was 0, 1, 1. The unit tangent vector was 2/3, 2/3, 1/3. And so the dot product between those two things is going to be 0 plus 2/3 plus 1/3. So you end up with 3/3 or 1. Okay? And so now we know that a sub t equals 1. We know that t equals this vector 2/3, 2/3, 1/3, third. And this is all for t equals 0. So next we want to find a sub n. And so to find a sub n, we essentially want to find a sub n by saying, well, the magnitude of a minus a sub t, which is really, this, remember, is the same thing as a sub n, n. And so the magnitude of a sub n is a sub n itself. And so looking at this again at t equals 1, is going to be, well, a was the vector 0, 1, 1, minus a sub t was 1, times t at 1 was 2/3, 2/3, 1/3. And so doing that computation, this multiplied in is just going to be negative, negative, negative. And then we add the two vectors together. So 0 minus 2/3 is going to be minus 2/3. Then we have 1 minus 2/3 is going to be 1/3. And then 1 minus 1/3 is 2/3. Remember, we have to still find the magnitude of this. And so the magnitude of that is going to then be the square root of 2/3 squared, which is 4/9, plus 1/3 squared, which is 1/9, plus 2/3 squared, which is 4/9. And so what you end up getting here is 4/9 plus 1/9 plus 4/9 is 9/9, which is 1. Square root of 1 is 1. So a sub n is also 1. All right, last we need to find is n itself. We want to find n at 1, right? And so to find n at 1, what we really want to do is we want to take a sub n, n, and divide by a sub n, essentially canceling these out. Well, this is a sub n, n, which was this vector right in here that we found the magnitude of. And a sub n itself was 1. And so if we take this vector, negative 2/3, 1/3, 2/3, and divide it by 1, we get that same vector again. And so that is n of 1. And so a of 1 has to equal a sub t at 1 times t at 1 plus a sub n at 1 times n at 1. That's the decomposition. Well, a sub 1 was, what was that vector again? A sub 1 was 0, 1, 1. And so what we did is we decomposed it into a sub t, which was 1, times t, which was 2/3, 2/3, 1/3, plus a sub n at 1, which is 1 as well, times n at 1, which is negative 2/3, 1/3, 2/3. And so that is the full decomposition of this particular vector when t equals 1. So the acceleration was broken into these two parts, the tangential component and the normal component, acting in the change in the speed and the change in the direction.
Just we have to think about what we have in each case. Let's which one is which. The XY plane. This flat, here's the x-axis, here's the y-axis. Parabola here along it, we would match it up with that picture. In this case, we have all three squares. What do we have in each direction? Z squared equals 1, which means that direction, okay? And squared, or cover up the z, x squared minus y squared. Which direction or in the xy direction. So that's this hyperbola that we have here. This figure ends up matching up right here. One sheet, if you notice it's oriented along the y-axis because the y is the one that's different. So if I was to identify this, I could just match it up with this surface here, or I could label it as a hyperboloid of one sheet. It is going to be unique in that this parabola in the zx direction, the difference is this one is negative, so it's an upside down parabola. So we have an upward parabola, we have a downward parabola, depending on whether we're looking at z and x or z and y. Well, look at this, we have an upward parabola this way, and we have a downward parabola this way. This is to call it a hyperbolic paraboloid, but we can match this equation with this figure. The surfaces, what we're doing here is we're practicing looking at equations and what that equation would give us in 3D space. Of this cylindric surface that we started with here, and then we have these two, which were our quadric surfaces, two of our quadric surfaces. Do is if I gave you pictures and equations, be able to match them up. Something beneficial to you, and that's really what I'd be looking for come test time. Vector function give us some curve, okay? In this case, if I was to travel from a t value of 5 around this thing to a t, travel along this curve, I want to find that curve distance. So we have a simple way of doing that. The way we do that is by this formula. This to take the derivative of, we're going to get 1, we're going to get negative 3 sine t together, so 1 plus 9 sine squared. At the 9, you're left with sine squared t plus cosine squared t plus 9, because this is equal to 1, so the square root of 10. Time is square root of 10. We know that that's not always going to be a constant. Sometimes it's a function of t, sometimes it's a constant, something we talk. So subtract a negative to get 10. So we get 10 square root of 10 as our arc length. Here, that's what you're going to have to integrate. Again, not always a constant. Sometimes it's a constant, sometimes a function of t. Regardless of what it is, you need to be a function of t that you need to integrate, but again, integration should be no big deal at this point.